Okay, so let's get started. Your midterms will be, Alex is finishing the grading on your midterms right now, and so he should have them up this evening. People seem to think the test was hard, but the mean was higher than it often is for the second test, so I think people did pretty well. All right, so it was a week ago that we last had lecture material, and we were talking about the control of the respiratory system in particular. So I just have a few slides to wrap up on that front, and then we're going to talk about the cardiovascular system. And the context for thinking about both of these systems is how your body changes respiration and circulation in response to elevated metabolism or changes in metabolism. So once you get up after class and start walking around, then all the skeletal muscles that you use for that elevate their metabolic rate. They need ATP, they use glucose, they use fatty acids to do that. And that all requires more on the part of the respiratory system and the cardiovascular system. So we started that lecture considering this graph where you have somebody, a test subject, varying their exercise intensity and that having an effect on oxygen consumption. And then we see this very rapid rise in the rate of ventilation. And that helps explain how it's possible for the arterial side of your, that is the systemic arterial side of your circulatory system, to maintain a elevated or oxygenated partial pressure of O2 at about 100 millimeters of mercury, despite the fact that that increase in activity causes this drop here in the partial pressure of the venous return to your right heart. And so the question that we're pursuing here is how is this controlled? How is the what is the respiratory system monitoring for this control? What are the efferent organs, which is most of what we've talked about so far? And where are the integration centers? And we left off with that consideration of integration centers. And we stepped through this simple model of what a central pattern generator is. And even though that's really simplistic compared to the complexity of the network that's in the brain, it gives us a general sense for what these two dorsal and ventral respiratory groups do. And the activity of those two groups are governed by this third center in the brainstem, the pons, or the pons includes a region that is responsible for respiratory control. All right, so now we got integration centers and effector organs, all of those skeletal muscles that drive the respiratory mechanics that we see down in red down below. That just leaves the afferent side, the sensory side of our control system. So how does your brainstem become aware of what's going on, what matters to the respiratory system? And that's where we have chemoreceptors. And chemoreceptors in the periphery. Now, if you want to know how effective the lungs are at any given moment relative to the metabolic rate of your body, then it makes sense to monitor the arterial side of the circulatory system. And in fact, at the carotid artery, we have what's called the carotid body. And the carotid body includes these chemosensory cells that send information to the pons that then inform decisions about the respiratory rate. Also, there are comparable receptors in the aorta, okay, bundled in something called the aortic body. And the key cell type that's responsible for transducing information that is relevant to the respiratory system, those cells are called glomus cells. And glomus cells are pretty easy to understand given our mastery of our understanding for neurons. And so let's just consider how a glomus cell works here. So we've already considered how calcium influx facilitates the release of neurotransmitter in a presynaptic neuron. And so a glomus cell has that same dynamic here. This is an axon, a postsynaptic cell right here. And so this glomus cell is on the presynaptic side. And of course, the calcium release that we're used to thinking of in the neurons is triggered by an action potential of the membrane because those are voltage-gated channels. So glomus cells, like neurons, have potassium permeability, have potassium leak channels. Okay, so the goal here is to monitor something about the chemistry of the blood on the arterial side that is then going to be transmitted to the nervous system. So the partial pressure for O2 is what is providing a stimulus to these cells. And in particular, it is a drop in the partial pressure for O2. Okay, so if we think to respiration, if you elevate your metabolic rate, you're going to have more deoxygenated blood returning to the lungs. And if they don't reach that 100 millimeters of mercury on the exchange, then on the arterial side, you would see a slight drop. And bear in mind that we saw that basically the partial pressure for O2 looks flat in that exercise graph, but if you zoom in, you could see little oscillations because there is that capacity, like when you start intense exercise, that there's going to be a momentary, very tiny drop in the partial pressure for O2, and that's exactly what's happening right here. So that drop in partial pressure of O2 has what effect? Okay, so we're looking for something that's going to depolarize the membrane because we've got the voltage-gated calcium channels. And if we've got potassium involved, the way that that's achieved is that they reduce the permeability to potassium. Okay, so we have a depolarization not through using sodium, but just reducing potassium permeability. Question?
Okay, if you're gonna decrease O2, you're gonna partial pressure O2, you're gonna decrease the pH. So decreasing pH doesn't.
No. So pH is tied to CO2, not O2. But I like what you're thinking because wherever you have some kind of response to CO2, there's always the possibility for that to be actually a response to pH because they vary together. But in this case, we're talking about O2, and it's O2 that's going to affect potassium permeability. That depolarizes this membrane. We've got those voltage-gated calcium channels that respond to that depolarization and release a neurotransmitter. So that's a pretty straightforward way for the glomus cells to be sensitive to oxygen, provided that they have this capacity, this ability to vary potassium permeability in response to the partial pressure for O2. Okay, so that's a glomus cell, and we have glomus cells both in the carotid and aortic bodies, but there's also central chemoreception. So when we talked about thermoregulation, there were thermoreceptors in your skin, and they have an effect on shunting blood away from your skin. And then we had central thermoreceptors that have a more dramatic response, that is responding with shivering. And so here again, we see both peripheral receptors and also central chemoreceptors. And the way the central chemoreceptors work is they don't have those glomus cells that I just described, but instead it's cells in the brain that are directly responding. So in the brain, the neurons of the brain are separated from the circulatory system. So down here we have a bunch below this yellow line, we have a bunch of neurons in the brain. And the capillaries that feed nutrients to the brain and allow for gas exchange are separated by this space here that's filled of a fluid called the cerebrospinal fluid. And so to have a direct effect or a direct stimulus on cells in the medulla, it has to be mediated through the cerebrospinal fluid. So here we have an example of CO2 playing a role. CO2 in the blood diffuses into the cerebrospinal fluid. And then we have the same reaction in that fluid as we see in the blood. That is, they combine with water to produce carbonic acid, which yields bicarbonate and a proton. Okay, so that reaction is what accounts for the correlation between partial pressure of CO2 and pH. So wherever there's an elevated concentration of CO2, you end up producing more protons, which causes a drop in pH. Now, the reason why it's worth mentioning here is that the central chemoreceptors are directly affected by pH, and it's the protons that act on those chemoreceptors, which then stimulate our integrating center. All right, so again, it's a sensitivity to blood chemistry. It's chemoreception. It's just that it's mediated in a totally different way. Okay, in this case, it's CO2 that in turn affects pH of the the cerebrospinal fluid, whereas in the glomus cells we saw that it was all about oxygen. Okay, so what that means is that we have three potential sources of information in the blood that can influence the respiratory system. Okay, so we just talked about the glomus cells right here. That's the partial pressure for O2. Even though it's through the pH of the cerebrospinal fluid, we would say that the stimulus is carbon dioxide. We didn't talk about it, but CO2 also has an influence on the glomus cells, as does pH. And so all three of those are potential sources of information. Question?
How does the lowering of pH affect the integration centers again?
Do you mean
like before, in the slide before?
The slide before that? Yeah, so the lowering of pH in the cerebrospinal fluid would be in that arrow right there. So the stimulus is carbon dioxide. It just so happens that pH is the messenger. Okay.
And then that affects the pathway how again?
Well, we have pH-sensitive receptors in the cells in the medulla, and we just leave it like that. It's just it's a black box. Okay, so what we just added was how all of these efferent actors, all of these muscles in the respiratory mechanics, function to boost ventilation. Okay, so when the CPG rises up in its rate and intensity, then descending commands from these dorsal and ventral respiratory groups activate those muscles to get either an increase in the ventilation rate, or actually both, they tend to be correlated, or the tidal volume. Okay, so let's consider what happens when you increase metabolism. Okay, so this is when you're getting up after class and hurrying off to the next thing. There'll be a momentary elevation in the oxygen that you use up, and so you would expect a drop in the partial pressure for O2 and a very and at least a momentary rise in the partial pressure for CO2, and because CO2 goes up, then the blood pH goes down. So the pons indicates to those ventilatory groups that the ventilation rate should go up, and so it increases the rate and the tidal volume. As a result, the ventilatory rate elevates because of all of the respiratory mechanics that we detailed before. And then that is all going to have a negative effect. So if you remember that hyperventilation graph that we looked at, that where you have a rise and a leveling off of the partial pressure for O2 and a drop and a leveling off for the partial pressure for carbon dioxide, just keep that in mind because that's how ventilation in turn influences the partial pressures in the alveoli, which is in turn reflected in the blood. So the bottom line here is that increases in ventilation are largely driven by that increase in the partial pressure for CO2 and a drop in the partial pressure for O2. Now, one confounding factor here is that you have the ability to control these muscles. You can force your lungs to breathe at a higher rate. You can actively increase ventilation. And another thing that happens is that your forebrain will recognize if you're about to be very active. So for example, if you're about to sprint in a race, and you're waiting for that starting gun to go off, your body begins to elevate ventilation in anticipation of that. So this is the feedback that we have when we just allow for this less conscious control. Whereas we also, when we're exercising, can increase ventilation rate in anticipation. So it can be a little bit more complicated than this, but these mechanisms are always at work. Okay, so for hyperventilation, that is if you're, this could be after you're done exercising and your respiratory rate is still very high, even though your metabolism is starting to wind down, or you force yourself to breathe at a higher rate than necessary, then your respiratory system is delivering more oxygen, it's offloading more carbon dioxide than you truly need for your ventilatory rate. So when that happens, as we saw in that graph of the partial pressure as a function of ventilation, then we have this elevated partial pressure for O2. So think on the arterial side, more than 100 millimeters of mercury. We have a depression in the partial pressure for CO2 below, say, 40 millimeters of mercury, and an elevated pH as a consequence. So in order to maintain homeostasis, we want to wind down the activity of the respiratory system, so the pons gets involved and sends a signal to the respiratory groups to decrease ventilation through lower frequency, reduced tidal volume, and that in turn has a negative effect. So again, we see negative feedback, whether the stimulus is hot, pointed up, or pointed down. In both cases, negative feedback will help to achieve the homeostasis that we're seeking. And so decreases in ventilation are therefore largely driven by the partial pressure for CO2 and PO2. pH, even though it can factor into how the glomus cells work, is a relatively minor player. So this would be sort of a small box. All right, so that sort of completes the story for all of the both afferent sensory side, the integration center, and the efferent center. And so that helps us explain how, with this increase in the intensity of exercise and the increase in O2 consumption, that the body is capable of maintaining that partial pressure for O2. And because of this control, it maintains that O2 despite the fact that there's increased demand and there's also faster blood flow through the lungs. Despite all of that, the arterial side maintains that constant partial pressure for O2. Okay, any questions on respiration? Yes?
Can you go back to the last? Yeah, so from the graph, are we having the two negative feedback here, or like both the blue one and the green one?
Are there, is the question is whether there's negative feedback on the blue part?
Yeah, like you are giving like two negative signs in this one.
Two negative signs where?
Yeah. So one for
Oh, and then the one on that right there?
yeah. So if there are like two negative feedback, isn't like it's actually a positive feedback for the dorsal respiration?
So the argument here is that maybe you sort of get a positive because you've got two negatives in a way. Yeah, that's not the case, but I can imagine reaching that interpretation. And so you just have to be careful on how you decode this kind of iconography. So what's intended here, first of all, just on the afferent side, all of these arrows are basically just a reporting of sensory information. So you don't have any negative effects here. You could imagine that maybe if the partial pressure for CO2 is relatively low, then you could imagine that the signal is going to be maybe lower than it would have been, at a higher rate. Then the way to interpret this little negative here is that it is reducing the activity of these two respiratory groups. So it's reducing it down. Then, and in a way, that negative is sort of has a different meaning than this negative up here, because this negative means that these efferent actions, which in this case is a reduction in ventilation, by reducing ventilation, we're going to tend to counter the stimulus. So that negative is actually totally consistent with that negative. They don't sort of cancel each other out, or like one acts in the opposite direction. It's not like you're multiplying two negatives to get a positive or something like that. It's instead that this is just consistent, or because of this, you end up getting that, but then that also depends on the sign of that. So in this case, if your ventilation goes down, then instead of having a high partial pressure for O2, it's going to tend to, that high partial pressure is going to reduce. And same thing with the low partial pressure for CO2, it's not going to be as low once the ventilation goes down. Mm-hmm. Yeah?
So on this graph, it says that pH is directly affecting the peripheral chemoreceptors.
Right, which we didn't detail.
Yeah.
Yeah.
Why would it not? I thought that if it would affect one more directly, it'd be the central chemoreceptors because of what you said about hydrogen protein.
Yeah, yeah. So again, that's a little bit of a convention. So, I'm saying that the way that that the blood CO2, because it's really the CO2 that's in the blood that's providing the stimulus for both of these systems. And the fact that protons are the messengers of the partial pressure for CO2 in the cerebral spinal fluid, that's sort of a technicality, because it's not the pH in the blood that's activating the medulla. It's instead the CO2. It's a CO2 that's diffusing across into the cerebral spinal fluid. So that's why I'm saying that pH is in the arrow here and not a stimulus. And it's because the blood pH doesn't directly affect the central chemoreceptors that we don't have an arrow from pH to down here. Yeah. Okay. Just give me a second. I'm going to switch the slides over to the cardiovascular system.